similar topic. And so it's nice to see sort of, 2 years later where we are, what do we think, have the opinions changed? So I'm looking forward to the discussions here.
Also, I guess quickly, Dieter, if you want to say some words. Is he there?
You have to unmute yourself,
Yeah,
Dieter.
there we go. Sorry. Dieter Fox. I'm on a shared position as faculty at University of Washington and at NVIDIA. I'm broadly interested in robotics, perception, manipulation, and as such, of course, very interested in kind of these combinations between deep learning and structural approaches from robotics.
Cool, thanks. So let's just have a quick introduction, I guess, of the panelists. And when you introduce yourself, could you just also give maybe a quick 30-second or a 1-minute summary of the talk that you had given for the workshop that are, I guess, already up on YouTube. So go ahead. Maybe Jeanette, do you want to start?
Sure, I can start. Thank you very much for inviting me to this workshop. I think I was also at the first version of this workshop in 2018, which was a lot of fun and still in person. So, well, here we are. I'm a professor at Stanford. I work on robotics. I mostly am interested in manipulation and grasping, and specifically when using partial information coming from real sensors like vision, touch sensors, things like that. And yeah, I've been really interested in structure because I found that this is what actually makes learning on a robot actually really work and constrains it. But I have no idea what structure is the right one, but I've definitely tried a bunch of those. And in the talk that I've submitted to this workshop, which is pre-recorded on that YouTube channel, as Arun said, I'm focusing a bit more on structured action representations because we found in some of our work that this makes a huge difference for learning approaches, what kind of space you actually learn in and how you hierarchically decompose it. We actually used we designed the hierarchy in our approaches. I know, for example, I'm looking at Carol right now. He has been working on more learned hierarchical approaches, which is very interesting. But yeah, it actually does make a huge difference. So people should think about these structured action representations as well, and not only about the perception side, maybe, which is also very interesting.
Great, thanks. Thanks for that. Jitendra?
Hi, I'm Jitendra Malik. Most of my career, I worked in computer vision. Last few years, I've been dabbling in robotics. Actually, I dabbled a bit in the 90s in self-driving cars as well. So I strongly believe in models and intermediate representations. And my talk tried to make a couple of claims. One was that we shouldn't just do direct training from pixels to talks, that intermediate representations have value. And we had some work which was showing that what kinds of representations to build up from vision. And so that the learning could go much faster on top of those representations, which embody essentially some implicit knowledge of the world. My second thesis was that I really like imitation learning. I think it's a paradigm for a lot of what goes on in biological motor learning. And but to make that practical, you ideally want to have the ability to learn from observing other people in a very natural setting. So ideally YouTube videos. So we have developed some technology which effectively goes some way in that direction.
Great, thanks, Jitendra. Maybe Carol, do you want to go next?
Yeah, sure. Hi, everyone. Thanks for inviting me to this workshop. My name is Karol Hausman. I'm a research scientist at Google Brain. And I work on robot learning, I guess, as everybody here. More specifically, lately, I've been really interested in multitask deep reinforcement learning. And in my talk, I talked a little bit about what it would take to make robotics a fully data-driven field. That would allow us to make progress not only from incorporating better and better priors, but also from just scaling things up. And in particular, I bring up 3 different lines of work. So first, we try to see whether the hypothesis that if we train on a large enough data set on a broad enough task, then the right structure can emerge is true also in robotics, and it seems to be the case. And then we also look into what kind of structural approaches or what kind of approaches can we bring to robotics such that we can tap into more data sources. And I think that would be kind of one way of unclogging that pipeline so that we can scale up robotics significantly by just tapping into more data. And then lastly, I talk a little bit about how we can generate data in a scalable way using some informational theoretical criteria so that we can just leave the robots alone in the room and they'll figure out kind of the interesting things to do there. And I hope that if we do all of these things, then we will have this other avenue of progress in robotics, which is we can get better by just scaling things up.
Awesome. Leslie?
I'm Leslie Kelbling at MIT. I've been working on robots and learning for a long time. The thing that I talked about in my talk and that I'm most motivated by right now is trying to understand how to design a kind of a compositional, and now I was just thinking about it, a kind of a constructive architecture for learning very complicated systems of skills and perceptual abilities and so on. So can we make a robot that could pose itself its own little localized RL problems, then learn models of the skills that it acquires that way, use the models it has to do planning, do exploration using those learned skills to reach farther, pose itself new questions, learn new skills with RL, model those skills. And in a kind of constructive and continual and compositional way, build up an enormous set of abilities. And you could imagine this sort of story going across multiple robots. I like very much Jitendra's view, first of all, that the vision process, you know, in brains, it's not the same as the skill learning process. It happens in different places with different architectural priors. The idea that we might start this from an understanding of some notion of objects and properties. And also that imitation, of course, it can't be sufficient because I don't know what it feels like to do something from a YouTube video, but watching a YouTube video could give me the idea that it might be possible to juggle. And once I have the idea that it might be possible to juggle, then maybe I can set myself a motor learning problem of doing that. So compositional learning architecture, that's what I want.
Awesome. Yeah, thanks so much for those nice summaries. We actually, I think, have Nicholas, who's one of the co-organizers as well. He just joined lately. So Nicholas, could you just give a quick intro of yourself, I guess?
Hi. Yes, so I'm Nicholas. I'm also a research scientist at DeepMind, as Arun and Marcus. And so my background is actually computer vision. And like a long time ago, I worked on basically probabilistic models for images. And there I was sort of pursuing a mixed structured connectionist approach. So we had some structure built into our models. And I think sort of this legacy has stuck with me, and I'm trying to apply similar ideas now to sort of architectures for motor control, or really sort of for the full sort of, I guess, perception, reasoning, action pipeline. And I'm specifically interested in the representations of behavior and how we can learn them, and what sort of the weak inductive biases are, such that with a little bit of structure that we impose and learning, we can. I'm having some connectivity problems here. We can get both sort of skilled, agile, and also reusable behavior.
Great, thanks, Nicholas. So let's, if any of the poster presenters from the first session are here, you can just quickly, unmute yourself, maybe just introduce yourself for a few seconds.
Yeah, hi, I'm Krishna, and I'm a PhD student at Mila, University of Montreal. And I really believe in structure, and I'm working on how we can leverage all the rules that we've learned about or we've studied in terms of, physics simulation or image formation, like graphics and computer vision, and trying to connect them to robot perception and action.
Hey, everyone. My name is Iman, and I'm really excited being in this workshop. I'm a newcomer PhD student at University of Freiburg, working with Wolfgang Burger on learning the dynamics of real world in an unsupervised and structured way. Really looking forward.
Awesome. So, I mean, if there's anyone else, you can just raise your hands as well in the Zoom chat so that we know it and we can quickly call on you.
Hi, everyone.
Hey, go ahead.
Hi, I'm Sasha, Sasha Salter. I'm a PhD student at the A2I laboratory, Oxford. And my specialism is in achieving robustness and generalization for reinforcement learning in robotics. Primarily, we've done this through structure, either at the hierarchical compositional level or the work at this conference here is using attention mechanisms and leveraging privileged information available during simulation and training to achieve those traits. So thank you.
Thanks, Sasha. Michael?
Yeah, hi, I'm Michael. I'm a PhD student at the Technical University of Darmstadt with Jan Peters, and I mostly work on inductive biases, and I really wonder how can we use structure from physics, from control theory with learning to actually get robuster models and better generalization.
Great, thanks. Alina?
Okay, hi, I'm Alina. I'm a PhD student with Jeanette. And we've been working on differentiable filters. And actually, in the work that we present here, we've done a lot of experiments to basically provide lots of advice for researchers that want to use those differentiable filters for their next project.
Awesome. Matt?
Hi, everyone. My name is Matt Halm, and I'm a PhD student at the GRASP Lab, working with Professor Michael Poza. We also have Sam Frommer, who will be co-presenting the poster in here, who's a computer science undergrad in our group. And a lot of the work that I focus on is understanding, how the sort of problematic natures of friction and contact, like discontinuity and non-uniqueness, interplay with the inductive biases in deep learning, and how we can actually leverage knowledge from mechanical theory to make our deep learning projects that have robots that use contact more effective.
Great, thanks. Neha?
Hi, I'm Neha. I'm an AI resident at Facebook. I work closely with Franzi as well. We are presenting our work on learning state-dependent losses, so introducing more structure in meta-learning approaches. Yeah, so I'm really looking forward to this workshop. This is my first workshop, so I'm really excited.
Nice, great to have you here. Harshit?
Hi, I'm Harshit. I'm a master student at Carnegie Mellon. So I'm interested in offline RL, model-based RL, and inverse RL sort of intersection. And in this workshop, we'll be presenting our work where we show how online planning methods in RL, which typically rely on fixed horizon, can be extended to reason for future returns. Yeah, this is my first workshop as well. I'm excited to be here.
Great, and last, Kristen, sorry.
Sorry, I'm trying to get my video to work. Hi, I'm Kristen Morris. I work with Franziska Meyer and Neha Das. I work at Facebook AI Research, and we're going to be presenting our poster on learning state-dependent losses for inverse dynamics learning.
Great. Cool. So let's now, I guess, go with questions for the panel. So so if anyone has questions for the panel, just again, as currently, just raise your hand in Zoom, and we'll call out. I can, I guess, start with one of the questions that I have. So we really, pretty much all of us know that structure is, I guess, in some form great, but it's really hard to explicitly define what structure actually is, right? I think everyone pretty much has their own definition for this. So, I'd like to know what, I guess, all the panelists think structure is. Actually, Carol, I mean, if you want to start this, because I thought that you had a very interesting definition of this, or very interesting, I guess, approach to this in your talk. Do you mind?
Yeah, so I think my view may be a little bit different than from what I've heard in other talks. So I think commonly we understand structure as some kind of way to introduce bias to our algorithms, so that we limit the kind of hypothesis space, and this allows us predominantly for more efficient learning. And we've been doing this quite a bit in robotics, I feel like. And dependent on the specific problem setting and so on, we can very clearly show how putting the right structure for that problem setting makes learning much more efficient. Often it also leads to better generalization, but to better generalization within that problem setting. And I think I think there's also this other kind of structure that I think about, which is the structure that emerges once you train on big enough data set. So we've seen this in something like computer vision, where we train on ImageNet and you train a fairly simple but very capable model on it. There are certain features that emerge from that model that actually transfer really well to other tasks. So it seems that there is some kind of structure that the model was able to capture so that it generalizes to other visual tasks, sometimes even to robotics tasks. So I think that kind of first line of thinking about structure as a way to make things more efficient might not be necessarily the one that amounts to the most progress. And to me, the reasoning there is that if we really want to evaluate these priors and the structure that we put in to make things more efficient, we would need to really do it on a big enough problem and a big enough data set. Otherwise, we are just kind of switching from problem to problem, and it's really difficult to kind of have very general conclusions about which priors are good and which ones aren't. So even if we had that view that we need structure to make it much more efficient, we would still need a really big data set and a really general problem setting to even evaluate whether the priors we came up with are right. And we've seen this also in computer vision, for example. We had convolutional neural networks for a really long time. I think in 1988, there was LeNet-5 that was already quite similar to the convolutional architectures that we have today. But it took 24 years to 2012 to realize that this is kind of the right structure and it scales really well with data, because that's when we had the big enough data set to kind of tell us that this is the right prior. So if we need really big data sets and really general problem settings to evaluate whether the priors are right, then we might as well collect these data sets and try approaches that leverage these data sets. So I'm a big fan of approaches that allow us to kind of tap into more data sources so that we can take advantage of data coming from different tasks, from different robots, collected in completely different environments. And I think this way, the right structure will emerge.
Cool. Yeah, I mean, Jitendra also in his talk said something about YouTube, for example, right? And I guess the learning features, let's say, from YouTube for something like third-party imitation learning. So I think that could potentially be something as well. Does anyone else in the panel have any thoughts on this?
I want to argue with Carol just a little bit. I would argue that Jan knew that convolution was the right structure. We didn't need data to know that. We knew it because of, well, at least we had a good idea, because in fact, brains do a computation that's kind of like that, because we all understand that those invariant properties of images, people have understood for years and years and years and years that translational invariance and all those things are important. So I think there are some, and I don't think priors are a thing that is borne out experimentally. Priors are a thing that is a fact about the world that you live in. Now, the problem is that we engineers are bad at taking facts about the world and encoding them into computational structures. And so I agree that there's still a lot of, we can all say, oh, we live in a world where there's gravity and matter coheres into lumps. And I'm gonna always have my robot living in a world where there's gravity and matter coheres into lumps, but it might be difficult for me to understand how to materialize that fact about the world into a program so that the program can leverage it. So I think the idea that priors are an empirical thing seems kind of funny to me. The idea that though we need a lot of practice and testing and data and whatever to decide if we've put them into the program in the right way, I think that that's right.
Yeah, so maybe if I can just quickly respond to this. Yeah, I think this is a really good point. So I think there's actually two problems there. Like first, it's not only that we don't know how to put how to encode these priors, but I think very often we don't fully understand what these priors are. We think that we do. So for example, the notion of objects, it seems kind of very obvious and kind of the natural reaction to go, we understand the world as objects that we manipulate. But I think if we expand the kind of the types of scenarios that we will be dealing with in robotics, then even the notion of objects becomes really tricky, right? Like it's, for example, a bike can be considered a one object, a bike, or a bunch of objects depending on the task you're doing if you want to fix a bike. And I don't know, an ice cube, when it's melting, it's even difficult to say when the object starts and when it ends. And there's so many different aspects to objects that makes it so difficult for us to understand what it means for an object to be an object. You know, if you have an onion that you cut, suddenly it becomes all kinds of different objects, but it was one object before and all kinds of things like that. So first, we don't fully understand how these priors work, even though we have this mirage that we do. And second of all, yeah, it's really hard to encode them. But if the right structure emerges from the data, then if there is some kind of notion of objects to be learned, then it will emerge, and it will be already incorporated in our learning algorithm kind of perfectly. It's kind of the difference between telling your intern or your student kind of what to do versus having them figure that out on their own. And they have then full understanding of why it came about and how it connects with everything else.
So,
yeah. So,
if I could jump in. Sorry,
Jitendra, go ahead.
Yeah, so to add to what's been said, I think one angle is thinking about the constraints on the world. So this is essentially like the Gibsonian perspective, that we live in a special kind of world, and those constraints are bound to affect our perceptual and motor worlds. It's a concept. I mean, if we lived on Mars, some things would be different. If we live underwater, things would be different, right? So that has to come in. And there's obviously this game of what to build in and what to learn from data. I want to emphasize one other aspect, which I think is more common in the computer vision work, but I've seen less effectively in the robotics work, which is that we really need to think about many tasks at the same time. When we focus on one task, honestly, pixels to talks is perfectly fine. It is really that we really need to be considering zillions of tasks. So therefore, compositionality that Leslie referred to, transferability, modularity, all those good, solid engineering values, they matter a lot more when you have to consider a lot of different tasks. So I would argue that a big insight in computer vision, which was a surprising one, which was not obvious from just the fact that Lynette is you could argue, in fact, that Lynette has predecessors. I mean, Fukushima's neocognitron. It's really Hubel-Wiesel 1960, okay? What was interesting was that we trained these architectures, and the architecture for classification was helpful for object detection. The kinds of feature layers which were developed, starting with Gabor filters and various levels of abstraction of the visual world, they turned out to be useful for many tasks. Now, we've built up on this theme by trying to explicitly consider the space of tasks and how different tasks help each other. But what's that corresponding taxonomy, if you will, hierarchy, heterarchy, whatever it is, in the motor space, right? There has to be that, because it cannot be that there are 500 motor tasks, each with its own special motor area. That's not the case in the neuroscience, right? Just like in vision, we have zillions of tasks, but there is a hierarchy with 10, 15, 20 areas which does the job across the board for a very wide range of visual tasks. The same has to be true in motor. But we have not, we as scientists have not been able to capture that adequately. Okay, so there has to be the counterpart of the ConvNet plus on the motor side, right? I mean, I think these are symmetric problems. Perception is like many degrees of freedom going to few, and motor is the other way about. But I think you guys have to get your act together and solve this. Okay.
Awesome. I think Nicholas and Jeanette, they've both raised their hands. Nicholas, do you want to go first quickly?
I think I can keep it really short because basically what I wanted to say has already been said. So I think my first point was that maybe when one of my questions was, what's the ConvNet of motor control and behavior, maybe more generally. And then I think I was thinking going beyond that, basically going beyond sort of very simple but very effective priors like convolutions. I think overall we haven't been that successful at identifying these a priori, even in other areas and building them in. Yeah, but so I'm just mirroring basically what people have already responded.
Yeah, Jeanette?
Yes, thank you. Yeah, I just want to respond. I guess like I have two things. A response to Carol or more a question is like, you said that you think if we could extract the priors from data instead of hand designing them, then we can get rid of our faults as engineers of defining these priors or of our difficulties of actually defining them, right? But I'm not so sure about this, right? Because structures that we may extract from data may be defined by the tasks that we want to do with that data, right? And then there are lots of things that we as engineers put in place in order to extract that kind of structure. Task is maybe even just one of them, right? And I'm just wondering why you think extracting from data will remove that problem of us being also somewhat biased, right? And having to engineer this. And I have a response to Jitendra as well about the action representation, but maybe Carol can talk first about this.
Sure. Yeah, so I don't necessarily vouch for us solving one specific task, let's say some broad task like grasping, and hoping that we'll learn all kinds of priors from that and then using this to solve all of robotics. But what data-driven techniques allow us to do is to collect all kinds of data from all kinds of different tasks and learn the right priors that encapsulate all of those. Right, so I think we need to, I fully agree with Jitendra that we have to move away from single tasks, but we need to work on our algorithms such that if we had enough data and if we had data coming from all kinds of different robots, from different robotic labs, from different tasks, environments, kinematic structures, and so on, and we were able to have algorithms that can take advantage of that very diverse data set, then the right priors will emerge.
Okay.
So, yeah.
Sorry, yeah, so maybe since you pointed also to Jitendra's point, I just want to talk about that a little bit, about the ConvNet of action representation, maybe. So what we found empirically, and maybe it's kind of logical, but we actually empirically tested it, is that dependent on the task, also the action representation matters, right? So for example, if you do a task that is just free space motion and you have to track a trajectory in a very specific way. Let's say for a person, it's like doing a tennis swing or golf swing or something like this, then actually controlling or even having the policy learn to output in joint space is much better than if you, for example, output anything in end effector space, maybe with variable impedance. But then if you want to do a manipulation task that involves a lot of contacts and where you really have to control the forces you apply, and you have to deal with noisy perception where you actually don't want to be stiff but compliant to give in safely to unexpected contact, then actually learning a policy that outputs in end effector space, maybe also the impedance gains, has a huge advantage over learning in joint space, right? Like whether it's torque or position or, you know, velocities, whatever. And also yesterday, I was in this other workshop on learning task and motion planning. And there also Mark asked the question, well, you came up with something about object-centric representations, also coming back to Carol's point there. But maybe not all the tasks need an object-centric representation, right? Some tasks you may want to actually control the velocity of the object, maybe pushing it with a certain force so that the object has a specific velocity, right? And then object-centric is maybe not the right thing that you want to optimize over, right? So every task really has different action spaces. And while we analyze this empirically, that it really makes a difference for the learning, for the learned policy, or for learning the policy, it makes a difference what you wanted to output. We don't have an idea on how to automatically kind of switch between it or how to pick maybe that representation. So that's on the ConfNet of action representations. There are many different options, but we haven't just uncovered that lower layer, right, of like picking this.
So I think Nicholas and Leslie have both raised their hands. I'll just say something quickly. So in the end, it's not like we want to optimize our representations for each of those tasks, right? We sort of want to work on all of the tasks well.
Sure. I also agree with that point. We want to do all of the tasks, but I'm saying we've done a lot of tasks and they all benefit from a different action representation, right? So
I totally agree with that. But I guess all I'm saying is maybe when we look at this multitask thing where we're actually thinking about optimizing at the same time for all those tasks, it might be okay to lose in some so that you gain in others. And a general purpose system, I don't think you can expect it to do extremely well on all those tasks, right, at the same time.
I would like that though.
I mean, at least us as humans, I know, can do certain things good and cannot.
I agree.
So there are trade-offs.
Sure.
Sorry, let me go to Nicholas first and then to Leslie.
Just one quick note. This is Dieter. Just I've been raising my hand also for a while. Maybe you don't have me on your screen.
I don't see you. Yeah, it's weird.
How should we do
blue
this?
hand in the chat.
Wait, there's a
in the participants box.
Yeah, in the Zoom.
Okay, that's what I should use. Okay.
Yeah, sorry. I should have said this earlier. Yeah, Nicholas, sorry, go ahead. Or Dieter, actually, if you...
Dieter should go first, yes.
Yeah, go ahead.
I don't know.
I actually did see him.
I can see you now.
Hands, but I didn't make
Sorry. You raised your hands now. So.
Yeah, because I saw some people raising actually their hands in the video, and then you saw that, so maybe they did both. Yeah, I just want to say that I feel like we are really barely at the beginning of understanding of what these structural priors might look like that we actually should inject into these systems, right? So on the one side, you have the extreme case where we're making, let's say, model-based approaches differentiable and thereby have some kind of course, very strong structure in these systems. On the other hand, you might just have some high-level kind of contrastive loss training on these systems. And I think we just, and also related to Jitendra, I totally agree that we need to look at maybe more complex and more variety of tasks, because otherwise there's always just a big risk that we're going to overfit to one specific representation, right? As Janet also said, for example, whatever, 60 pose might be good, depending on which reference frame you're choosing of the object, the gripper, joint space. We just don't know what these should look like. So we have to make sure that the task on which we train these systems force the learner to actually come up with all these different representations potentially, right? So, because if you ever, for example, train a system and say, well, I think 60 pose of the object is the right representation, you impose very, very strong constraints and limit other abilities to learn maybe more powerful and interesting representations. So, and in that respect, I also think actually that simulation is a very nice tool, at least for exploring that space. I'm not saying that this will make everything work immediately in the real world. We had discussions on that yesterday, but it's just kind of to explore the space of structural kind of priors and how can we inject this kind of knowledge into into our robots. And we keep on seeing this also, even still also in computer vision, right? Where you see many really nice papers like the SimCLR work by Hinton, where they show extremely powerful embedding learning approaches. And often the papers contain, let's say, certain pieces that they think were really important to make their embedding learning approach as powerful as it is. And then there's a follow-up paper that says, oh, by the way, we didn't really need all of this. So I think even in vision, we just don't know yet what this looks like. And in the end, maybe we will figure out how to do this without too much prior structure imposing manually, let's say, right? But I think it's just not clear yet where we go. And robotics is just extremely complex, especially through the 3D reasoning that is inherent in the problem.
Nice. Leslie, I think you had some.
Well, sure. I like the idea of thinking about what's the moral equivalent of the ConvNet on the motor control side. And certainly people who studied motor control in actual animals have thought about basis sets of control abilities or something that could be composed to build up more complicated structures. That's something that we haven't really pursued all that much in robotics. I think partly because the underlying control of a robot is just so different than the underlying control of a natural system with all the tendons and muscles and so on. But really thinking more about motor bases and the idea also, I mean, one thing that I think came up in what Jeanette said, and also something Carol said in reaction to what I said before, is I think there need to be multitudes. I think that for any problem or model, there will need to be so much flexibility in the representations that end up being brought to bear on any particular task, right? So it's quite clear that you can't have just convnets or just object-oriented this or just admissive, some particular kind of control. That the ability to do all of these things somehow has to be latent in this machine. And maybe we learn that. I mean, I think, of course, Carol's right. No one can argue because evolution did this job that we were all hoping to do. So it's totally possible. And the question is only what do we greedy people want to do in the short term that will be faster than evolution. But I think if we are going to engineer things, the idea that we engineer bases of representation, bases of control a little bit, and then let the system figure out how to compose and apply them, maybe that's the way to go.
Great. Nicholas, I think you still have your hand raised. Do you want to say something, or?
I think, again, some of it has been said already. So I think what sort of in terms of data versus prior, I guess, clearly they can be seen as sort of two sides of the same coin. Maybe one question one can ask is what's easier to both specify and collect, right? So both, I mean, there's the question of what can I work with easily practically, where maybe data doesn't do so well, at least in robotics. But then there's also the question sort of what is more naturally, where do I have a more natural access to providing the right input, right? And maybe this is actually where data or specifying the set of tasks rates higher than sort of thinking about the structure a priori. Although it clearly has caveats, as we've just heard. And then the other point that Dieter made, actually, I would love to hear sort of maybe some other opinions on this, the value of simulation in understanding these questions, because I was kind of trying to ask the same question yesterday in the retrospectives workshop. And it's something that sort of occupies me a lot as someone who does a lot of work in simulation and very little on actual hardware. And then I guess sometimes wonders what's the usefulness of the things we're investigating there.
Carol, I think you have your hand raised. Go ahead, Carol.
Me? Okay.
Yeah.
So I wanted to refer to the previous point that Leslie and I think Dieter as well raised. So I also really like the idea of convolution for robotics, for the equivalent of this. But I'm trying to think how to make this a little bit more practical. So even if there exists something like this, let's assume there is, and we just need to discover it. I think the only way that we can evaluate whether whatever we discovered is right is to have this big data set, right, of robots doing all kinds of different things, and then putting that structure in and seeing whether things work better or not. I think it will be extremely hard to test it any other way, because otherwise it would be kind of all of the weight of this problem will be on that one person that develops that, or on that one lab or one group that develops that approach, and then they have to show it on, you know, on kind of some experimental setup, which will be probably constrained to a single robot doing a single task. So I think no matter which approach we take, whether it will be some kind of very creative, innovative structure, or whether it will be all data-driven, we still need to collect a lot of data either way. So I think one practical thing that could come out of this is that if we had some kind of repository where every experiment we do in all different labs, we just upload, you know, some standard data structure that says, you know, what kind of task the robot was doing, all the images that it's seen, all the actions that it produced, and so on. And I think if we have algorithms that can deal with that, then the right structure will emerge. But I might be wrong. But we need that data anyway, even if the other approach is the right one.
Cool. I mean, I think there are two other people who've raised their hands, but I just want to quickly say something like, do you think it's about more data, or is it about diverse data, right?
I think it's about diverse data, and it's about having our algorithms be able to cope with that diverse data. So I think often we just think that if we had a lot of data, if we had, you know, infinite amount of data, then all of robotics would be solved. And I'm not fully sure about this, because if we had all kinds of diverse data, if I know we had billions of data points right now with robots doing all kinds of different things, I don't think our algorithms today are capable of extracting the right things from the data and learning some kind of capable motor control from it. So I would like to work on structure that allows us to tap into more diverse data sources so that we can make progress that way.
Cool. So I have a bunch of people who've raised hands. I think Krishna, you had raised your hand.
Yeah. So it's like pretty exciting to hear all these insights. Like I'm probably going on a tangent here, but it's more of a question than an answer. Like, what do we do with all of the, you know, research that has been carried out over the last decade or so in terms of like model-based robotics with control, or, you know, their structure in the form that projective geometry was, you know, laid out, or study of image formation was carried out. Like, are those techniques still relevant, or do you see all of probabilistic robotics and so on just phasing out in the near future?
Okay, I think it's a great question. I think we have Jitendra and Dieter next, and I'm sure they can both answer these well. Jitendra.
Yeah, so I wanted to make a couple of points related to this thread of the multitude of tasks. So first of all, I think responding to an earlier comment by Janet, I don't think we needed to necessarily come out to one approach, but a relatively small number. I mean, if you use the term bases, relatively small number is enough. So in computer vision, I would argue that, I mean, I gave a talk like 5-7 years ago where I said that there are 3 R's, recognition, reconstruction, and reorganization. So sort of semantics, segmentation, or 3D geometry kind of task. And roughly speaking, these families cover a lot. So, I mean, obviously there are thousands of computer vision papers a year, but these broad families cover a lot, and then you can have variations in that theme. So my expectation for robotics would also be that it's not that there's one single answer. I mean, obviously, first of all, we have the distinction between actions of the hand and actions of the feet. So manipulation versus locomotion. Then within manipulation, there will be some subcategories, etc. So anyway, that's one remark to make. Second remark that I want to make is that about just data in general, and the situation in robotics and vision are not quite the same. See, in vision, we cheated, and we cheated badly. We cheated because we had this supervision available through AMT workers. This is not natural supervision. When a child is growing up, he or she does not get the supervision of 10,000, 1,000 categories, each with 1,000 examples that mom has dutifully labeled. That's not the way it works. They actually interact with very few objects, but they interact with them very deeply. And they're doing it, it's all natural supervision, it's self-supervision. When you go to the robotic space, then the kind of data that people are typically talking about is, I don't know, simulation data, like, okay, OpenAI trying to learn how to do Rubik's Cube by zillions of trials in simulation. It's not the same kind of supervision. It's a very much weaker supervision. You get supervision at the end, yes, I succeeded or failed. Whereas the kind of supervision we have provided in computer vision system is very rich, and it's cheating. It really is cheating, because human babies do not have access to that kind of supervision. So unless you confront that, a direct copy of what works in computer vision is not going to go over in robotics.
Thanks, Jitendra. Dieter.
Yeah, I agree that the vision community, of course, had that big advantage of the cheating. I mean, you could even think about simulators being something like an equivalent of the cheating, where we could use these simulators to provide us some kind of supervision, right? That in the real world would be extremely difficult to get, right? So that might be one step maybe in that direction. I also just want to say that there's this focus on we need the ConvNet kind of structure for robotics. I think it goes beyond ConvNets, right? ConvNet is more like, let's say, the convolutional structure and invariants and things like that. But I think the big progresses being made in vision, in language processing, is really about these embeddings of words and of scenes, right? And I think that is something that we really need to aim at in robotics, where we need to learn some kind of vector space, graph-based embeddings of scenes, so that robots can reason about objects and transformations in a more general way. I think that's going to be very important. And there, of course, then the big question is, in contrast to computer vision, or a lot of the work in computer vision, in robotics, we have the advantage that we deal a lot with temporal data, right? Which means we have supervision through this, let's say, predictive learning, which in computer vision, often you look at images in a fully isolated way, right? And in our case, we have clearly this connection between one time step to the next and how it relates to action. So I think we need to learn to take better advantage of that. And I think it's not only about, let's say, reward or not at the end of a trial, right? It's really about this dense data that you can use for temporal supervision. And maybe one note to probabilistic robotics. Well, I think reasoning about uncertainty is still going to be important all the time. Of course, now you hopefully that a lot of that will just emerge also through the policies that these systems learn, right? That they might not have explicit uncertainty reasoning, but they are robust to that because of the way they were trained and the way they kind of represent the environments in these embeddings. Is it already obsolete? I don't think it's quite yet obsolete. I think coming from also the practical world of getting robots to actually do things in the real world robustly, I think these kind of model-based approaches clearly still have their place, and we can enhance them with learning-based approaches to make them actually robust. So I think the combination of these is going to be important. And on the very long run, who knows, maybe we can learn it all.
Awesome. I think, Marcus, you had raised your hand.
Yeah, I had nearly taken it down again because Dieter and Jitendra already iterated over that. But there's another question now from Ankur that connects to what I had in mind quite strongly. So we have the situation that we have multiple tasks, like when we take Karo's perspective of learning from multitask data, we have the perspective of the representations that we have, we extract them from data, but the other question is the using our tasks for testing perspective, and like having a set of basis tasks that we're all interested in, and like having a sufficient set that we can actually test our algorithms with. And this is a huge challenge. And it would be interesting to get some feedback from our panelists on how they think, like in robotics, we as a community can better benchmark and evaluate the performance of the different representations that we either craft or that we learn on a set of tasks that interests all of us. And like this is something that in robotics has come up over and over again in like with Dieter's focus on simulation, where we can all benchmark against a very standardized environment, which is great, but then also with object data sets like YCB and so on. But it's always been challenging, and it would be interesting to think what our panelists think about the question of having a basis set of tasks to test with, and the problems that we have and how we could address them.
Cool. Well, Carol, is that an answer to what Marcus was saying?
Yeah, so working a little bit on multitask reinforcement learning, one thing I quickly realized is that actually coming up with tasks is one of the most difficult part of it. And it's actually really limiting. So if we kind of imagine this big data set that everybody will be collecting, and we'll be asking people to put some kind of labels of what task the robot was doing, I think it's very ambiguous often, and like it's even hard to come up with all of these tasks. So maybe I think there are ways to get away from that. For example, goal conditioned reinforcement learning or universal value functions, I think is one way where I think of it as like a unsupervised or an equivalent of unsupervised learning in the supervised learning scenario, where if we have big enough data set and if we're just learning how to reach a certain goal image, then not only we can take advantage of all of the data, we don't need the labels for all of the tasks, we don't need to come up with the tasks ourselves, and then to evaluate it, I guess there will be just like a set of goal images that you need to reach. And we can later on post hoc kind of develop the notion of what those tasks mean and what they are. But I think something like goal conditioned learning would allow us to kind of move away from that and take more advantage of our data.
Cool. Well, there's a bunch of people. I think Nicholas, you might be up next, and then Leslie.
Yeah, so my points are, so one, I've got a methodological question, whether we are making our lives unnecessarily hard at the moment, sort of trying to solve too many problems at the same time. Multitask learning, figuring out the right representations. Both are sort of, they clearly influence each other, and sort of maybe sort of trying to solve both the representation question and the question of with RL to solve many different tasks is just a bit too hard, and will limit. So we can't really distinguish failures then, whether it's because of the representation or whether it's because of the like otherwise problems with the algorithm. And I'm wondering sort of whether thinking more about techniques like imitation learning or perhaps offline batch RL approaches in this context would be particularly valuable, so that we can sort of separate a little bit the different dimensions of the problem. And then I had sort of maybe a remark about uncertainty. I actually think learned uncertainty is sort of, it's a bit narrow. I think it will get us pretty far in many cases, but at least sort of practical problems that we encounter a lot, even in the learning-based setting, is sort of how can we make our algorithms aware of what they don't know? And I guess learned uncertainty is not a solution to this. So I do think it's hard, and people have tried this in other contexts, sort of to incorporate maybe notions of uncertainty into connectionist approaches. But I do still think there's value in it if we can figure out how to do it. I'm not sure there is a good solution, but that's.
You're muted.
I am muted. Sorry, I was typing. Leslie, you're next. Sorry, and then Dieter.
So I think it's interesting. I backed up a little bit and listened to people talking about what tasks we should work on. And then there were all these words about methods. So I think if we're going to talk about tasks, we should talk about tasks and not mention methods at all. And then we're free to apply our methods to the degree that we want to apply them. So here's my favorite, and I have no trouble coming up with tasks. So let me come up with some. I'm going to start at the highest level and work down. The thing I really want, okay, I really want intelligent robots. Okay, I can't talk about that. So now the thing that I'm just fixated on, and many of you have heard me rant about it, is making a robot that could go to your house and make tea. Okay, so that's a little kind of confusing. I'd like to make a robot that could go to anybody's house and make tea. That's what I want. But we could make that even more kind of concrete. We could say, we'll take the fanciest simulator that, I don't know, Dieter and Jitendra and whoever are gonna make with a very, very complicated environment with fabric and liquid and objects and whatever. Big house, randomly procedurally generated houses filled with objects and fabric and liquid. And I should be able to give the robot an objective, let's say in natural language, just so that we don't prejudice the question at all, and it should be able to do it. So there's an infinity of tasks, and that's what we should think about. Okay, now I'm done.
Interesting. Dieter.
I agree that we have to, I actually like also like the whole setting of task and motion planning, right? Like what the community is coming up there with far more complex tasks than we typically see when we reason about lower level RL. I think Carol mentioned we should provide, and that triggered my response, my raised hands. Carol mentioned this kind of, goals should be defined as images. I'm actually against that, I think, because first of all, it's totally constraining the view. And I think that's an approach that might work for low level control tasks. But if you think about a more complex task and motion planning setting, an image of the goal is clearly insufficient. So at the same time, I think we do clearly need benchmarking and test and development environments that can be shared across researchers. I think otherwise, we're just going to be stuck not being able to compare our work and make the progress that you really see in computer vision going on, I think, significantly faster. And with respect to representing goals, I think we need to be open-minded to very different approaches. One way of, for example, representing goals might be through language commands, right? That is something that's being pursued a lot by vision AI nowadays, where in the 3D simulation environments, right? They look at language for specifying task for a robot. And also then, of course, actually they use task and motion planning in these environments to generate scenarios that then should be trained by a robot. So again, I think we need benchmark environments, and the whole task and motion planning setting seems like a good place to start, because that actually can solve pretty complex problems, at least in simulation for now, right? And the question is, how can we bring that to the real world?
Yeah, great points there. I mean, I always feel like everyone agrees that we need to have benchmarks, but nobody has a clear idea of how we're going to get there. That always seems to be something that comes up in pretty much all the workshops I've attended, at least. Jitendra, I think you're up next.
I want to speak to this. I think that we can get to some agreement on benchmark tasks in simulation. Specifically in the space of navigation, we were able to do that, right? So we were able to define some tasks like navigating to a point, navigating to some object, et cetera, and at least the computer vision-ish side of the community working on navigation sort of accepted those standards. And we did it by a community process. I think that's the thing about benchmarks. You can't just one person, one research group define this and accept everybody else to follow. You need to go through kind of this boarding community process of trying to get to a consensus. But all the good benchmarks in computer vision, like Pascal and Coco and so on, have been arrived at that way. So that's a one remark I would make. Second remark I want to make about tasks is I totally like the tea. Here's my cup of tea. So I totally agree with Leslie on that. What I want to say is, again, is you must have real perception in each of those tasks. So my critique of the robotics community in the old days was that a lot of tasks like motion planning or so on were set up in a way where you totally knew the environment a priori, right? And then, all this clever work on going back to John Canny and stuff, right? But it really didn't deal with the world as we perceive it. Whereas I think robotics just like me as a computer vision person, just doing perception is doing something quite silly because perception has to be coupled with action. Similarly, on the robotic side, just doing action without assuming real world perception is equally silly. I mean, we really need to be together on this, okay? We all need to accept this as axiomatic. So real world perception will bring real world errors and you have to deal with that. So I think so I think simulation environments are here to stay. And even if there is a sim to real gap, they will enable us to explore the space of tasks much more easily than we could with each task in the real robotics laboratory setting. So I do think that's something that simulation will help us with.
Great. Jeanette, I think you'd raise your hand.
I think Carol was actually earlier than me, but I'm happy to
okay.
take over. Okay, so first on Jitendra, what Jitendra just said, like I think simulation environments are here to stay, and they also always have been here. So it's not that we just started to magically come up with simulation environments. We always use them to sanity check, at least, right? So maybe to Nicolas' point that he raised earlier, what is simulation offering? I do agree that it offers to prototype stuff, right? And to just, I mean, why would anything work in the real world if it doesn't even work in simulation, right? That's kind of the first question. But the danger of simulation is that you come up with problems that either don't, that you don't need to solve in the real world, or that don't even exist in the real world, right? That you cannot get diverged if you don't route back to the robotics world. Like one of the problems of most of the simulation environments out there is that you can step the simulation with your algorithm, right? So it's totally fine to need whatever time for computation, which is super annoying. And I think that goes against what the problem is in robotics, which is time is just running. It's your adversarial. So that's my point on simulation. And then the thing about benchmarks, I'm really divided on benchmarks because on the one hand, yes, okay, in computer vision, they really kind of streamlined the field on very specific problems, and it made it possible to compare approaches, which is nice. But I also, yeah, I don't want to throw a lot of shade on the computer vision community, but I've been to a few computer vision conferences and I'm really, really bored. I'm really, really bored. I'm really sorry to say that, but it's basically the problems are already defined because this is what the benchmarks are. It's like, okay, it's object detection, which is important. These are important problems. I'm not saying they are not important. I'm just saying that it's only these problems, right? And I feel like in robotics, I feel very happy to be in this community because we're so creative and we come up with like problems like making tea with this robot, or I don't know, juggling or balancing something or bringing a car on the road, right? And clearly it needs these computer vision problems to be solved as well, and getting better at this. But I also like, in a way, that we are unconstrained by benchmarks on which we're all running against this one goal. We have all these creative people with all sorts of backgrounds, right? And I love this about robotics. And I think this would go away a bit. And yeah, so that's kind of, so I'm a bit divided on the benchmarking part there. One more thing about simulation. I think one nice thing about simulation is that two things, what it's used for. You can actually generate partial sensory data, right, in a controlled way and generate this data. Although most people, I think a lot of people are using it with full state observation in this moment, like in all the OpenAI gym tasks, I think have been mostly used with that, which is kind of weird. While actually simulation offers to generate partial sensory data to solve the really hard problem, which is mapping, processing this partial sensory data. And then also often what I found is that even if you have analytical models, they're typically very slow. So you could use learning to learn faster, like computationally faster forward models so that you can actually use them on the real robot. Of course, there's the sim to real gap
I mean, that's another topic, which was another workshop. Let's not talk about that maybe. Okay, so yeah, these are my my points on benchmarking and simulation.
Cool. So let's go to Carol and then Jitendra, and we have to switch to the poster session after that. Carol.
I just wanted to quickly reply to Dieter's comments about goal conditional learning. And I fully agree that the goal images are not practical at all to specify the task. But I think there are two problems to be solved. One is, how do we create algorithms that can extract as much from these big diverse data sets as possible? And I think something like universal value functions or goal conditional learning could do that. And then the second problem is, how do we interface our robots? So what is the right interface? And I would hope that if we have the right set of algorithms for the first problem, then the interface question will be much simpler. So we can then, given that you learn the right embeddings that kind of represent the motor control and kind of intent of what you would want to achieve, then maybe if you take a BERT model that learns some kind of notion of language and connect the two, it would be relatively easy to then have an intuitive interface to control your robot to do anything in the world. And then one other point about the assimilation, I agree with Jeanette, and I think that actually real data benchmarks could make a lot of our problems easier. And this is a little counterintuitive. I think that it would allow us to work on the right set of problems. So things such as what Jeanette mentioned, that the time passes and you have a certain amount of time to do your computation and so on. But we also get a lot of diversity for free that is actually really difficult to generate in simulation in a way that reflects the real world, because it's not necessarily IID. There's all kinds of different things that happen in the real world, and we'll have to deal with them one way or another. So we might as well have a lot of data collected in the real world that we need to deal with. We will have all this diversity coming from people uploading all kinds of different things that happen in their labs, and then we don't even have to worry about sim to real gap. So not only it gives us the right problems to work on, but it will also be a little easier, I think.
Cool, thanks, Carol. Jitendra?
Yes, so since Jeanette has thrown shade on the computer vision community, I must rise to the defense of my folks. Okay, so there's this old line from Newton: if I've seen further than others, it's because I've stood on the shoulder of giants. We need to make progress additive, and to make progress additive, we need to cluster the problem space into some problems we regard as important and some problems we regard as exotica. So if we take a physics example, I mean, Galileo worried about balls rolling down inclined planes, but he didn't worry about the shape of a puddle if some milk spills on the floor. I mean, that's also a physics problem, but we don't worry about that one. Okay, if you look at biology, they focused on certain model organisms, Drosophila, C. elegans, etc., etc. Why? Because there is just so much to do, and we'll have to, every problem has its peculiarities, and by focusing on a few, our work becomes more additive, because I can use stuff that somebody else has done already, and those things I don't need to rediscover. So I believe that for additivity in science, we really need to focus our energies, because even though we have lots of robotics researchers, we do not have infinitely many. And focusing on certain tasks leads to a certain additivity. There is, again, I think this is a line from Rutherford, which is that there is true science and then there is stamp collecting. So robotics, I'm afraid, I'm sorry, now I'm throwing shade on robotics, okay? Gets into stamp collecting. It's exotica. It's like building this beautiful, delicious eclair. And I'm all for beautiful, delicious eclairs, but science is done with meat and potatoes. I need to have my main course. I need to have that first before I get to this beautiful, sweet, delicious eclairs.
Interesting point, Jitendra. Last Dieter, I think we have to go ahead. I think we'll stop after that.
Which is very, very, very briefly that I think, of course, the truth is somewhere in the middle, right? Where on the one hand side, sometimes I think the vision community is a bit over-constrained by some of these problems, which means you almost can't get a paper accepted unless you beat everybody on exactly the benchmarks, right? And that forces people often to work exactly only on these benchmark problems. But at the same time, in robotics, and I totally agree with Jitendra that we often do rely on, oh, my problem is slightly different from this other problem, and therefore I don't need to compare it anymore, right? I just do my own little thing and show that it's cool. And I think we need to get away from that. One very quick note, especially that I want to mention, is simulation versus real robot testing and all of that. Of course, real robot testing is great. The limitation is you don't get as much supervision, but I think another important advantage of simulation is kind of like a democratization aspect, right? Where right now there's only a very small number of labs that can afford to buy all the robots, to hire all the engineers to run these robots and do these experiments, right? So that's really limiting who can do this kind of work. And simulation is something at least where it's much easier to contribute to that on the research side then.
Cool. That's a great point. Nicholas, I think we might have to move this to the poster session because we're running a bit late. Sorry. So yeah, thanks so much for all the interesting points. I mean, like my 2 cents, at least on benchmarks, they definitely help in some sense. I mean, computer vision has definitely made a lot of progress, but at some point you end up chasing numbers. And I think that is what you see quite a bit in computer vision at these points. Of course, not having them at the same time also means that pretty much everyone can do their own thing, right? And you can still write papers. And I think somewhat coming up with some middle ground there would be cool. Maybe Nicholas, I don't know if this is what you wanted to say.
No, I wanted, so now you've shut me down so that you can make your point. I just wanted to say, apart from the benchmarking part, right? I think the other part is the shared resources or the reusability that sort of it allows many people to work on the same thing, right? I think this is another important aspect of benchmarks. They're expensive to build, at least at the larger scale. So I think someone needs to do it so that other people who have fewer resources maybe can sort of tap into this.
Cool. Great. So yeah, thanks so much for all the interesting discussions. I'm just going to have the poster presenters give a quick, I guess, 1 minute of each of their, or 30 seconds of each of their slides before we switch to the poster sessions. If any of the panelists have to head out, I think that's fine as well. I'm sure that Jitendra or Dieter might have time constraints.
Thank you very much for organizing this. It was fun.
Yeah, thanks so much for attending, Jitendra.
Thank you very much.
I'm just going to quickly share my screen so that I've let's see. Okay. So cool. Can you see these slides? Can you see this grad slam thing on top?
Yes.
Cool. So as soon as I go to this, can the poster presenter just give a quick sort of 30 second summary of this so that we can then go to the poster session?
Yeah. Hi, I'm Krishna, and I'm going to be presenting Grad Slam, Automatically Differentiable Slam. So in this, we propose a fully differentiable, dense SLAM system and show that this can actually be used to impose structure about all the things we know about 3D reconstruction and SLAM into deep learning frameworks. Excited to see you all.
Awesome, thanks. Next is hindsight for foresight. Iman?
Thank you, Arun. We humans have the remarkable ability to effectively interact with unseen objects by leveraging intuitive model of physics, which we learn from experience. To enable robots to autonomously gain this intuitive model of physics in real world, we present a structured approach for modeling the dynamics of a robot's interactions directly from unlabeled 3D point clouds and images. We show that our formulation leads to interpretable models for Visumoto control and planning. We're really excited to share more about this with you. Please come by our poster. It is named Hindsight for Foresight. Thank you.
Awesome. Neha?
Hi. So our work claims that meta-learning, a loss function whose parameters depend on the current robot configuration, outperforms all standard MSE losses and other meta-learned losses when we are adapting a learned model for inverse dynamics to a novel scenario. And we test this hypothesis on a KUKA arm. We basically trained a state-dependent loss function on a data set that is collected by moving the joints in a sine motion. And we then adapt an inverse dynamics model using this loss on a different data distribution from a pick and place task. And we show that this model outperforms models adapted using other losses, including other standard and MSE losses.
Awesome, thanks. Alina?
Hi. Can you hear me?
Yeah.
Yeah, okay. I guess the title already says it all. So in this paper, basically, we look at differentiable Bayesian filters, and basically they have already been shown to work very nicely for state estimation, but they're pretty difficult to implement if you want to use them for your own project. So we did a lot of experiments to make it easier for you to use differentiable filters if you want to.
Awesome, that's nice to hear. Sasha?
Hi, everyone. In our work, we introduced April, attention privilege reinforcement learning, to address some limitations of domain randomization for transfer, such as poor sample efficiency, asymptotic performance, and generalization to out-of-distribution held-out domains. April achieves robust and generalizable policies via the use of privileged information and self-attention mechanisms during training. We compare against competitive baselines on various domains, with April strongly outperforming. Excited to see you later.
Awesome. Nicholas?
Hi, everyone. So in this work, we present LCINet, which is a novel neural network structure which enables expressive stochastic transition dynamics models to be efficiently learned and used for planning based on locally connected layers within the related weights. It exploits locality and applies a learned transition to the original states while learning a model that depends on pairs of abstract states and actions. To demonstrate its advantages, we replaced the forward propagation module of QMBTNet with LCINet and compared against the original in a COMDT setting. And we found that simply replacing the forward propagation module with LCINet greatly improved success rate, regeneralization capability improved by up to 10 times.
Awesome. Next is Michael.
So in this paper, we're looking a bit at physics-inspired models for real-world systems, because if you have a physics-inspired model, you have hard constraints, but your real-world system is not really compliant with these constraints. And in this workshop paper, we are benchmarking roughly 26 black box plus white box models on real-world systems and see how well they perform for long-term prediction.
Great. And then Harshit? Are you there, Harshit? Okay, I think we might skip ahead then. Michael?
Yeah, so resampling is a key component in particle filters, but particle resampling is non-differentiable. We present a novel network architecture, the particle transformer for particle resampling. Incorporated into a differentiable particle filter, our model can be end-to-end optimized jointly with other particle filter components via gradient descent.
Awesome. Cool. So I think that's pretty much it. So this is the GatherTown link we're gonna meet in. Before I guess we go there though, I'm just gonna show you, just give you I guess a quick tutorial on how GatherTown works. So once you click that link, you're gonna essentially spawn your avatar here. And then the poster session is right in front of you. Just go through that door there. There's pretty much nothing else in the rest of the space. So you can just go into the space. That's going to give you, this particular area where there's going to be numbered posters. So if you just go next to a poster, you're going to see a preview. And then if you press X, you should be able to just read the entire poster. I'm going to ask all the poster presenters to stand right next to their poster so they can essentially do screen shares. You can also mute your video, mute your audio, and reduce your interaction distance. This sort of reduces how many people you're talking to at the same time. Note that if you're around a poster, if someone screen shares, you're just going to see it. That's kind of how the space is set up. Last but not least, before you go there, make sure to mute your Zoom audio, because otherwise you're going to hear a lot of feedback. Michael, do you have a question or?
I think you might have missed one of the posters.
Oh, I see. For this session, or is it the next one?
I think
it says the first one on the website.
Oh, I think that's not on this session though. I believe that's in the second poster session.
You are the organizer. I think it's listed on the first one on the website.
Yes, but I already, I believe, sent out the numbers.
Yeah, so I think you
splitting the
included
posters.
my poster in this session instead of the second one. So there might have been a swap.
Okay. Well, I don't have your poster number. It's 1, you said, right? So here, I think, is this the one? Or what's the poster ID?
For whose poster?
Sorry?
Yes, I think this one might be.
So all the posters are in the poster session, so you can obviously just go and present your poster there as well. But if you can tell me the number of your poster, the number that's listed on the website, then I can please go to that slide and you can explain it quickly.
All right, so my poster is number 15 on the website.
Okay. Yeah, so I believe this was on the second session, but go ahead.
Oh, okay. So this is work with Sam Frommer, who is also going to be here to explain the poster. So this is a project on learning dynamics. And you know, we've seen for many years in robotics that a good dynamics model enables good control and good planning. But you know, learning it from data enables you to not rely on a priori information about the environment. And when learning dynamics, there's fundamental bias variance trade-off, and learning an unstructured equations of motion as a deep neural network has the promise of being low bias. But in the case of frictional contact, even just the basic implicit bias of deep learning, which is smoothness, is actually biased against what we believe the underlying dynamics to be. So this method presents a different way of parameterizing dynamics that actually correlates smoothness with model simplicity and uses that bias effectively.
Cool. So I'm going to stop sharing my screen so that I believe Marcus should have posted the link to the poster session on the chat window. So just go ahead and you can join the chat session. Sorry, the Gather Town session. So we'll meet here again in about 30 minutes for the second panel session.
All right. Welcome back, everyone. I hope you can see and hear me. Let me first welcome a new round of speakers. In this session, we are welcoming, let me see if this works out. We're welcoming Peter Beal, Byron Boots, Rachel Eckerson, and Thomas Funkhouser. And just like we did in the first session, it would be great to start this one with the first introduction from each of our panelists and what structured approaches to robot learning, or what structure in general means to them, how it connects to their work. And I think if this is possible, if everyone is in right now, we could start with Thomas Funkhouser. Thomas, can you hear me?
Yes, I can. Can you hear me?
Perfect. Yeah, welcome.
Okay. Hi. Yeah. So I was a professor at Princeton for 20-something years and now work at Google. I come from computer graphics through vision and an interloper into robotics. The talk that I gave as part of this workshop was about implicit functions, so learning 3D shapes and from implicit represented as deep implicit functions. And for me, in that context, structure is the latent space you learn, combining with how to decompose objects to most effectively learn local implicit functions that combine into a global shape.
Okay, thank you. We can directly move on to Raquel.
Hey everyone, so I'm Raquel Hurtazo and I'm Chief Scientist for VerityG, as well as a professor at the University of Toronto. So in this talk, I talk about how to build interpretable neuromotion planners that can be trained end to end and basically operate from raw sensor data to the end decision. But by, as I mentioned, speeding out also these interpretable representations that are important for safety as well as validation and testing. And in this context, the structure comes in the representations, the intermediate representations, as well as the output representations, as well as all the prior knowledge that you encode in these models in order for the planners to be able, for example, to guarantee safety.
Okay, thank you very much. Next up would be Byron.
Hey everyone, I'm Byron Boots. I'm an associate professor at University of Washington. I recently moved here from Georgia Tech. I'm generally interested in researching machine learning and robotics and work at the intersection of both of these fields. Structure is clearly extremely important for machine learning. In my mind, structure can take many forms. So it might be the structure of a policy class. It might be the type of data that is presented to a machine learning algorithm. It might be the form of the loss function or cost function. It might be the way that the robot interacts with the environment or with a human teacher. So the whole key is, and it might be prior knowledge, right? Physics, simulator, things like this. And so the whole key is trying to figure out how to leverage structure, how to use it in conjunction with data in order to achieve the task that we care about for robotics problems. So I'm interested in all of these different areas and all the different ways you can kind of combine structure and prior knowledge with data in order to get an effective learning algorithm and get robots to actually act effectively on tasks in the real world.
All right, thank you, Byron. Finally, Peter.
Hey, thanks for having me. I'm Peter Abiel. I'm a professor at Berkeley and a founder of Covariant. Generally, I work in robot learning. How can we make robots do more interesting things thanks to learning rather than hard coding? So in the context of this workshop, the presentation I recorded was on investigating the question whether we can learn equally fast from pixel values as we can from having access to state. And I think, state is kind of the underlying structure that is something everybody in controls tries to exploit. That's the minimal representation of the world to help you predict the future. And so the question we've been investigating is, how do you get to the same efficiency from pixels, given you know that under the hood, there is a state. So even if in pixels, it's 1,000,000 pixels, if under the hood, the state is only 10 variables, then in principle, you should be able to learn very fast because you only really have to learn about 10 variables, not 1,000,000 variables, if there's 1,000,000 pixels. So that's something I've been very interested in. And under the hood, it brings together self-supervised learning and reinforcement learning. But at a high level, I think what really matters is the question, how do you learn as efficiently from high dimensional inputs when the underlying state is still low dimensional?
All right, thank you very much. So we're going to start with one question now into the session. And for everybody who's attending, if you got any questions, just like in the first session, you got a raise your hand function in Zoom. If that does not work out, simply quickly ping in the chat. And the question I would...
Marcus,
Hello?
sorry, just a quick thing. I think if we have some of the poster presenters for session 2, just quickly introduce themselves and maybe give a quick 10-second intro of them, that would also be nice before we can start the session.
That sounds good. Do we have a list, or is everybody in the session? Arun, you're muted again.
I'm sorry. People are raising hands. I'll just call them in sequence.
That's
Achin Jain.
Hi everyone. I'm Achin Jain. I'm currently working as an applied scientist in the computer vision team at AWS, and I recently graduated, finished my PhD in electrical engineering from UPenn, where I was advised by Professor Manfred Morari. During my PhD, I worked at the intersection of control theory, optimization, machine learning with applications to building energy optimization and autonomous racing. And during the poster session, I'll discuss our work on learning-based MPC for autonomous racing. Thank you.
Next is Sasha Lambert.
Hi, can you hear me? Yeah, hi, I'm Sasha Lambert. I'm a student, PhD robotics candidate at Georgia Tech, working with Byron Boots, my advisor, and Fabio Ramos over at NVIDIA currently. And I'm generally interested in control theory and for model predictive control tasks specifically, and perception. And in our poster presentation, we're looking at how to incorporate structure to actually help new variational inference methodology to scale to robotics problems that we're interested in, specifically in stochastic optimal control.
Great, thanks. Next is Gilwu.
Hi, everyone. I'm Gil Lee. I'm a PhD student at University of Washington. I'm advised by Sis Srinivasa. I'm mainly interested in representing model uncertainty as Bayesian reinforcement learning and bringing in techniques in optimal control or other model-based knowledge and connecting them to reinforcement learning in a scalable manner.
Great, thanks. Next is Rogerio Bonatti.
Hi, everybody. I'm Rogerio Bonatti. I'm a PhD student at CMU in robotics with Sebastian Scher. And a lot of my research has revolved around learning behaviors for robust real-life performance, usually for flying vehicles. So I did work on learning artistic principles for autonomous cinematography using drones. And in the poster session today, it's actually a slightly different topic. I'm going to talk about learning representations that can transfer from simulation to real life for autonomous drone racing. So I can answer more questions later.
Thanks. Next is Mengyuan.
Hi, I just graduated from Stanford, where I worked with Professor Jeanette Pope, and I joined GoogleX, the Everyday Robotics Project. My research in Stanford focuses on using computer vision and machine learning in manipulation, and especially in manipulating ropes. And in this workshop, I'm presenting our work that combines knot theory and reinforcement learning for motion planning to tie a knot.
Great, and I think last is Harshit.
Hi, I'm Harshit. I'm a master's student at Carnegie Mellon. I'm interested in offline RL and inverse RL. In the next poster session, we'll be presenting our work on how you can extract the reward functions when you are given just the expert state density. Yeah.
Well, Marcus.
All right, sure. Let's go ahead. Now, we've seen for this workshop that we have a quite mixed attendance and many also as junior researchers. One thing that we were not able to squeeze into the last session is the question, what would your advice be for a young researcher or a researcher from a different field to start at the intersection of robotics and machine learning? For example, Peter, would you have any suggestions?
Sure. Let's see. It's kind of complicated. It's a very fast-moving field, so it's very hard to say, okay, this is or that is what you should pay attention to and try to write a paper on. But there are a couple of maybe high-level advice that I can give. One of them is, and this is more general. I'll give one that's more general and one that's specific to maybe robot learning. I'd say generally, whenever I get new students involved, I tend to think through how their interests match up with more senior students and postdocs' interests. And I think often the most effective first 1 or even 2 years of PhD is to have a junior student collaborate with various different senior students and postdocs and learn from every collaborator they have that's more senior, a wide range of different, in some sense, tastes of what makes for interesting research, what makes for exciting problems, as well as execution styles on how to, work on a project and take it to publication. And so that's one of the things I spend a lot of time on in terms of, getting students started. in terms of specifically robot learning, I think one of the things you might want to think about is kind of, let's say 5 or 10, or maybe even let's say 20 years from now, what are the things that you think for sure have to be true about robots in the world at that time? And so you might already agree, well, definitely they will be learning at all times, because how could you imagine having a robot 20 years from now that's not learning? And then you're like, okay, you're already in the right place. You're going to work on something that actually matters for something that's going to be in the world 20 years from now. But then from there, you might also ask questions, to which extent will they be learning in simulation? To which extent will they be learning in the real world? To which extent will they be learning from demonstrations? And I think if you think kind of further into the future, it's often easier to reach conclusions about what definitely has to be there. For example, in 2011, I believe, or 2012, there was the Ikra Sushi Challenge. This is a challenge where a robot had to serve dishes in a fake restaurant. It was in Minnesota, Ikra, that year, and we participated. And we did okay in the challenge, but nobody in the challenge did anything that was amazing. That would hint at a working system of any kind being readily available. But the conclusion for us was that leading up to the challenge, spending all the time trying to get this to work, is that it was nothing but patchwork. Like, to get this to work, it was patchwork after patchwork after patchwork. And it made us conclude to revisit reinforcement learning, actually, because I'd worked a lot on reinforcement learning during my PhD. Then first 4 years at Berkeley, a lot of learning from demonstrations, but less reinforcement learning. But in that moment, we concluded we should get back into reinforcement learning, because we can't keep giving demonstrations, keep doing that patchwork. There has to be RL component to it. And happened to be very good timing, because 2013 is when deep reinforcement learning happened to start working. But it was driven for us from trying to get some real system working and experiencing all the things that clearly are not right and painful and should be fixed in the future of robotics. So maybe I'll stop there.
So if I can give my 2 cents, maybe. So I think my first advice would be also general, which is about don't try to answer all the questions in your first project. Right? A robotic system is very, very complicated, right? And so my advice would be to try to carve out a project where you tackle something that is concrete, right? And at the same time, you have the other pieces so you can demonstrate what you're trying to do. If you try to build all the software stack and everything for your first robot, it's going to take you many years to get there. Right? So I think that's one where whether it's existing code that exists out there or somebody in the lab, as particularly as more senior students, I think that's a great way to get your hands dirty. But don't go for I want to solve all these things, because that's too hard. And in terms of areas of focus, I think there is like 2 main directions that I think are going to be very important, or are more important now. They will continue to be important. One is planning under uncertainty, and how to handle uncertainty, how to define uncertainty. I think is something that is very open and very exciting. And the second one is how you actually test the system so that you can say certify this thing is going to do the right thing and it's not going to cause any hazards, particularly in safety critical applications, whether it's big robots or self-driving cars or whatever it is. So simulation, Peter mentioned this, but also even the metrics themselves, right? How are we going to say that this is actually doing the right thing? So I think these are areas where there is a lot to do, and definitely potentially could be good.
All right. Thank you, Raquel, and thank you, Peter. Thomas, would you like to add something?
Oh, sure. So I think there's 2 different ways that I found useful to choose problems. One is to set a goal that's maybe outside the range of things that are obvious to be able to do, and then figure out methods that are going to achieve that goal, which requires you to invent new methods. And the other is to take some skill you have that's unique to you and figure out how to apply that most effectively. So an example of the first one is with this project Tossing Bot, where we just set this goal that we wanted robots to be able to do taken place by throwing the objects into boxes. And we had to figure out ways to actually make that work, which led us to just to proposing residual physics, where you do a physical simulation and then you have the network predict the residual with respect to that. So that was a goal first kind of project. In the talk I gave today, it would be a method first kind of thing, where they basically said in computer vision, people are arriving on implicit functions as a way to represent things, where it isn't like an autoencoder where you have an input and then you encode it and then you decode it to an output, but rather the decoder takes in parameters that then compute the function. So like an inside-outside query or something like that. That's been incredibly valuable for computer vision and representing shapes, for example. And so I would ask the question now, how can you apply that for robotics? For example, what kinds of functions, like if I push here, what will happen? Or if I want to navigate, what will happen if I go here? That kind of thing. So representing things with an implicit function would be a method first kind of approach. Anyway, either of those could be successful, I think.
All right, thank you, Thomas. Finally, Byron, do you have anything to add?
Yeah, so everyone's given really great advice here, and I agree with pretty much all of it. So just a few things to add maybe. I like the idea of studying fundamentals when you're in grad school. So I think these fields move very, very rapidly, both robotics and machine learning. And so just making sure that you take courses in and try to understand basic tools and concepts from optimization, reinforcement learning, machine learning, applied math, controls. Like there's so many great fields to be drawing from, and grad school is a chance to really get this like broad, solid background that will serve you very well as these fields change. So I think that's one thing I just wanted to mention that others had not mentioned. I agree with a lot of what everyone else said. So I think, actually working with a real robot will inform you as to what is really difficult and what is easy. You might be very surprised. Setting achievable goals when you're starting out, but also be thinking longer term, kind of where do we want to go? I think these are all great ideas. I also sometimes think about research in kind of a model predictive control way, where I sort of forward simulate like many different possible ways that this research might turn out and different directions I might go in. But then, you should have this longer view when you should be thinking about this sort of thing, but also not be afraid to change directions based on what you see, papers that you read, what you've experienced when you're in the lab. So being flexible and adaptable seems really great as well. And just not being afraid to reevaluate what you've thought in the past and kind of update the way that you think about a problem. So those are a few things. I mean, there's all sorts of lessons to learn. And I think, just talking with other grad students and postdocs and professors, taking courses which are maybe a little bit outside your area, and learning from, engineers, mathematicians, computer scientists, and thinking about the different ways that they think about problems, and just being open to the fact that they may know a lot more than you about certain things, and you can learn from them. I think this is all very important.
All right, thank you, everyone. I think particularly this mix of different opinions here is very helpful. And after this kind of broad overview, I think we can more or less start into the topic of the workshop again. Again, if anybody has questions to raise, just use the Slack interface. And we can directly start with Arun potentially.
Sure. I mean, I guess thinking back on Byron's point, right? So in the last session, we had a question from someone who asked whether in the era of, I guess, deep learning, does a lot of the traditional methods like, I don't know, projective geometry, let's say in computer vision, or optimization or things like that, are a lot of these, I guess, moot, right? And do we really need to focus on some of these? I mean, this is of course, not in spirit with not in line, I guess, with the spirit of the workshop. I personally at least believe that it's not, but I would like to hear, I guess, your thoughts on these.
I think all of this is super important. So I don't think that, you know, I think you can be using like a deep learning approach to try to solve some of these problems, but I don't see how you wouldn't be served well to, you know, understand projective geometry. Like the ability to sort of understand how light and physics works and how, you know, the fundamentals of geometry, like all of this just seems like at a minimum good background knowledge, but I think can also inform the way that you design, you know, incorporate structure into neural networks, the way that you might want to think about generating data, like all sorts of things. So, well, it may not be, but I don't know. I think it's super important. And I think that it will help you to potentially develop better, more efficient approaches. So it's my view.
I have something to add to that, which is that I think we think of deep networks as these, you know, universal function approximators that they can represent any function and learn it, you know, immediately, and they're amazing. But it's not true at all. There's just certain kinds of functions that they can learn easily and quickly, and others that they can't learn at all because they fall into local minima, or, you know, it's not that they couldn't represent the function approximately, but it's that the current optimizers aren't able to learn it. And so I think the whole thing about robotics is to use models and what we know about physics and light transport and things like that to turn the deep learning problem into one that deep networks are good at. They're good at recognizing local patterns in pixels, and they're maybe good at classifying into a small number of discrete classes, but they're not good at going from, say, an image to an arbitrary abstract regression value. You know, and so we need to use what we know about the world to turn the problems into ones that deep networks are good at.
So same as everybody else, absolutely yes. I guess why would you ask the network to learn what you already know? Isn't it difficult enough to learn what you don't know? So I think combining this prior knowledge that you have in your representations, I think it's definitely a good idea. Now you can do this in many different ways in neural networks. You don't need to compromise, right? You can just combine the power of two things that are very powerful. For example, you can have operations inspired by physics, for example, in terms of geometry, and the way you compute your kernels, in the way that you fuse information across different sensors, for example, that they are related by geometrical properties. You can use things like differentiable renderers that allow you to learn in an unsupervised and nice way a whole bunch of different complex functions. For planning, optimization in the loop is important, right? We should go, to something that is more sophisticated than just feed-forward networks, right? So you can have these deep structure models where you learn through optimization functions, right? So I think there is so much that you can do by combining these concepts that's definitely the future.
I think I'm more torn on this than the rest of the panel. And I'll sound even more torn
no
on
kidding.
it to contrast with everybody else. I mean, obviously, it's no brainer that studying interesting things can train your brain, and it's a good study. And I think there's no contesting that you can build better working systems today by leveraging any kind of structure like projective geometry. It can help you with data augmentation, help you restructure your neural nets. But I think there is still a question to which extent that, is that fundamentally like building more intelligence, or are we just hard coding the intelligence? I mean, if I think about, some invariant that we haven't incorporated in a deep neural net, then of course we can think about how to incorporate it. But maybe, if you think about 10, 20 years from now, the best architectures then will maybe not be as closely designed by our insights, but be designed in other ways through, more automated mechanisms. And so I'm a bit torn on this because I'm pretty sure that to hit, best performance on current benchmarks, the only way to get there is to do, incorporate everything you can, not by necessarily architecting, because that's usually limiting, it's too strong an assumption, but by doing data augmentation on whatever you know. But in terms of 10 years from now, I'm less convinced that we'll rely on those things then to build the best possible systems.
So
all right.
I just follow up on this,
go ahead.
like pretty quickly, and maybe to challenge Peter a little bit on this. I think that one thing that I worry about is, okay, so if you have a lot of data, maybe you can use more general architectures, or you can think about how to automatically design architectures, or do things with a less prior knowledge. My worry though is that that the problem might get pushed to another place, like how data is collected, what sorts of problems we end up solving. So there are some problems where it's very difficult to collect data or very costly to collect data from the real world. And it feels to me like these are exactly the types of problems where structure becomes very important, because it allows us to generalize without having to pay those costs. And so, like, I think that for certain problems, sure, I think that we can set up automated data collection that allows us to collect truly massive amounts of data, and we don't necessarily need a lot of prior knowledge, but that's not all problems. And I think, maybe wrestling with this a little bit, like thinking about where can I collect data, how costly is it to collect data, how do I collect data, and how does structure play a role in all of that seems very important as well.
I like that notion of attaching a price to data collected, and see how much of the price tag you can reduce with things that are well understood, and to kind of see it as one big optimization of, what am I solving with data? What am I solving with prior knowledge? And together, getting to a system that's not too expensive to build, yet understanding, what is contributing what. I don't think we have a very good understanding of that today. I think it's a lot more ad hoc today than maybe we want to be at.
I think it's more than just data. I think that it's also about the optimization of the networks. You thought about the objective function that the network optimizer is trying to optimize. If you have a very complex task, then there's some local minimum that is really great and everything around it is bad, and there's all these other local minima. And without structure, you'll definitely fall in the wrong one and get stuck there. And so maybe 10 years from now, optimizers will be so much better that they avoid that, but it seems hard to imagine that, if as problems get more complex, that just by random search, you're going to find the right one.
All right, thanks.
Sorry, just to continue on that, right? I think even in the past panel session as well, we had some very similar discussions, and I think there was definitely a lot of emphasis, I think, on collecting more data and diverse data, and trying to see if, let's say, structure can emerge as opposed to sort of being hard-coded implicitly into the networks in some form, or into the training procedure and so on, right? And I think Carol was talking about this. He gave an example of, I guess, ImageNet having been trained on such large data so that the features that you get, for example, could be used for other tasks. And there was also talk of, can we find a similar, let's say, structure for robotics? But I'd just be curious to hear what everyone here thinks as well about something like this. Is data, or more diverse data, let's say, is that the answer as opposed to structure, or would structure, I guess, emerge, let's say, when you have enough data? What do the panelists think?
one thing maybe to think about is how long does it take humans to get some structure to emerge, right? And so if you think about basic things like grabbing an apple from a tree, seems like we can get enough data and it doesn't take too long for that structure to emerge. Then, you reach in, get the apple from the tree, and now you can eat it. On the other hand, if you look at something like Newtonian physics, like if you want to do precise control that relies on very specific calculations, that kind of thing took humanity a very long time to figure out how to do that. And so it seems that it could also depend on maybe the level of precision you want, that things that are fairly intuitive maybe can directly arise from the data, but things where you need high precision, say I want to send a rocket to Mars, I don't think I want to rely on a data-driven model to send the rocket to Mars. One, it's hard to get data for that. But in some sense, we have the data, right? I mean, Newton collected the data and hypothesized it would generalize to things like that, right? But it seems like our machine learning systems are not very good at that kind of generalization. And so maybe it's all about understanding what kind of generalization our current systems are able to extract. And some kind of generalization seems clearly out of reach for our current systems. If we don't put the structure in, it doesn't seem like it'll generalize in those ways. But in contrast, I think about something like ImageNet. If all I wanted is a robot to push objects around on a table, I could probably collect enough data for a robot to understand how to push objects around on a table. Not sure how much it would be. Would it be, tens of hours? Would it be hundreds of hours or thousands of hours? But somewhere in that range, there will probably be enough data to understand how to push yet another object to the end of the table.
That being said, it's not clear that it will discover the underlying 3D representations versus
that's true.
Do something less sophisticated, right? Which is sort of the question.
So another thing that this made me think of was just the role of interaction. So science in general, it seems like a very interactive process to me. I can propose, some hypothesis. I can test whether or not it makes sense. I can go back and refine, and then I can run some more experiments. And again, I think the way that data is collected seems important, and like the properties of the data set, especially if we want to come up with something which is, have the learning algorithm learn something which is very general and can be applied in many different types of situations. And again, I think that's, a type of structure, which is maybe as important as structure in the policy class. And I think this also gets to a point of like, how do you optimize, which seems important.
I think in the context of generalization that Peter also just right now brought up, it's kind of a big question of how we can test how far something generalizes other than just applying it to the task that we want to see that it generalizes to. And when we now treat research as this kind of progress that comes up with new structures that we can use, like we can take some of the algorithms that have been developed in classical robotics in the past that we can apply. We can train our machine learning models and apply something that has been pre-trained on ImageNet to use it for some other downstream task. It would be to see what kind of perspectives our panelists have on the question of how can we ensure that this process, actually that research progress, leads to tests where we can say we can really reuse whatever has been developed before. Like if we use mathematical equations, that will be very easy. If we use geometry, we just know that it underlies the fundamentals of the world. But how in other ways can we test that what we've developed we can use for as long as possible? I can potentially rephrase that question in the context of how can we best test the structures that we've developed? How can we ensure that this is something that benefits robotics, not just for the next 1 year, but for the next 5 years, for the next 10 years? How is it something that we can ensure has more long-term benefits.
I'm so curious
If that
about
is
the
an
answer to
answer
this question.
I can
It's
also
such a good
move on to
question.
another question.
I'm very curious what other people think.
I'm sorry, it's very high level. It's very abstract right now, but on purpose. What do you think, Peter?
Well, I mean, in some sense, the question comes down to how do you set a research agenda that's the maximally impactful research agenda, right? Which is a very hard question. I don't think any researcher claims to have the answer to that. Like everybody tries and tries to figure out what's hopefully an impactful direction to work in, and then often your students disagree and do something more interesting anyway. So, I mean, I think the way I think of it is think of things that have to be true 5 or 10 years down the line, that you're convinced of to be true 5 to 10 years down the line. So, for example, I think it's clear that 5 to 10 years down the line, pretty much all robots will have cameras and will do vision-based, maybe also other sensors, but do some kind of vision-based control. And so I think we think about, okay, what can I do that is very likely to have impact? Vision-based robotic control seems like a very natural direction to push. Now, to make that more specific, it's not very easy. Yeah, I think it's a very hard question to answer.
I originally was silent because I had 3 different answers depending on where you were in your question. At the beginning, I thought you were asking, how can we learn the next Newtonian physics from data? So is there going to be something where a computer looks at lots of data and then discovers F equals ma? That's what I first thought you were saying. And then I thought you were saying something about closer to what Peter said, which is, how can we pick something that is important, highly impactful, will be cited 50 years from now research. And somewhere in the middle, I thought that you were asking something about repeatability and can we develop components of systems that other people can use rather than we all develop our own robot system. Anyway, so I don't have a good answer to any of those questions, but I think maybe somewhere buried in your question was all 3 of those challenges.
Yes, absolutely. And whatever question would be most interesting for you would be the best to answer at that point. I think this kind of like, how can we benchmark our systems, which also came up in the first session quite a bit, is an important point in terms of how we can actually determine if something is beneficial. When I test something on my robot and you test something on your robot, there can be so many things that differ that are completely outside of our algorithms. And maybe we can push this question into a more practical direction. One thing that came up in the previous session, in the previous panel session, that was quite interesting was the discussion around simulation, and there's a strong benefit on simulation, which goes towards standardization. Everybody can test on the same environments. It connects to some of the benefits that maybe other communities like the vision community have, where you just have something, you can download it, you can run with it. It's somewhat comparable. And it would be interesting to see in this group of panelists right now, what are the perspectives to simulation? And maybe also where's a little bit of friction and where's something that simulation will potentially never help us do.
Let's see. So I will take this one first. So I thought, sorry to bring back your question. I thought you asked one more thing, which so the benchmark was part of it, but I thought you asked also. I interpreted as, can we have a dictionary of good ideas and for what they work, such that when you go and create your robot, you know where to pull, right? Such that you can create your solution to robotics. And I thought that was very interesting. And I guess it will be interesting to define what does that mean in the context of deep learning or robotics with learning. Anyway, so in terms of the benchmark, I think you're spot on. That I think we need a diverse set of robotic platforms that run in simulation. such that you can have reproducible results. And those of you that know me, I'm a big believer of benchmarks, right? I have done quite a few in the past. Now, the simulation, what is interesting is that you need to, for simulation to be very useful, you need to have a low fidelity gap with the real world. Otherwise, they're gonna end up, and the reason I say this is not necessarily for training. For training your systems, you can do domain adaptation, you can do a whole bunch of things, and it doesn't really matter that much. But if you want to validate a test and say my robot is safe, life is very different, right? And I think that if we are able to open source, a whole bunch of robotic platforms and environments with sophisticated, I guess tasks, I think we will go a long way. So 100% with you.
So I have a couple comments about simulation. I think simulation has a very interesting role. So simulation is basically using prior knowledge. So for example, in robotics, it might be physics, in order to conduct experiments so that you don't have to do it in the real world. And so like the way that I view simulation is something where we're taking structure or some sort of necessarily approximate model, and we're shortcutting having to collect data from our real robot or run a real world experiment. And this seems important because we are using physics and this prior knowledge in order to now generate data in a cost-effective way so that our machine learning algorithms may work better. And so I guess this is at least one perspective on it. And simulation can be used in a number of different ways. It can be used to pre-train a policy, for example, and then you can try to solve sim to real. It can be used in real time to predict what's going to happen at a particular state. But in my view, simulation is a pretty pure form of structure, which is being used in a machine learning or optimization framework in order to accelerate learning somehow or to make it more cost effective. I'm curious to see what other people sort of think about this, but this is my current view on simulation and its role.
I think benchmarks and even ones in simulation are a good thing, but they can be limiting in that they guide the community to solve those problems which may miss the boat. So if I remember correctly, Byron was training cars to drive quickly around tracks on like mud tracks that would be very difficult to produce a realistic simulation for. And so if you guide the whole community towards working on simulation problems, you might just end up deciding that the algorithms that solve easier problems are the better ones and never ever encounter kind of the real world complexity of the world, and therefore your robot system is really limited.
I want to double click on what Thomas just said. I think there's a lot of challenges ahead for us in building simulators that are capturing more and more of the complexities of real world compared to the simulators we have today. And we might be able to get much further than we are today. But right now there's a lot of limitations. And the one that most comes to mind is just the amount of variation that you encounter in a simulator. Whether you think about self-driving or robotic manipulation or other related problems, often the challenges are encountering the members of the long tail of possible things you could encounter in the real world. And it's proven hard so far, at least it seems so, to build simulators that also have this long fat tail of yet other things that you've not encountered yet, and all of a sudden there is something there. And so I think if we can get simulators to also do some of that, that would be really interesting.
So
right, thanks. Go ahead, please.
I think we should, to Thomas' point, I think we should take it as an opportunity, because releasing a benchmark is an opportunity to shape what's going to be worked on, right? So if you have a lot of thought before you do so, you can really push the community to work towards something that actually really matters in the real world, versus focusing on whatever problem they thought that maybe is interesting, right? So I take this as a as a plus plus. And I guess in terms of simulations and I think I think generic and long tail and adversarial stuff, I don't think it's so hard with simulation. But what deciding into how to test, how much to test from what is the real difficult problem if you want to really evaluate your system, right? But generating the scenarios per se is not necessarily super hard. Right. You can take it from real logs that you have collected in the world. For example, if you do self-driving, right? You have millions of miles. You have so many things you have observed, and you can generate specific tests by mixing reality with the world, with the simulation world. But how to decide how to grade, I think, is also very difficult.
I like this idea of sourcing the variation in the simulator directly from reality, and then have it be more reproducible because it's now in simulation.
Yeah,
I don't know how available that is beyond like in some big self-driving efforts though. But I really like that idea.
I think it's a challenge. We plan to release a simulator, so it's just gonna take a while. And
okay, well, exciting.
All right, yeah. So I think like algorithms and test environments or simulations are always being developed in parallel. So it's hard to say at one point where, like what would be an optimal environment, just because at the same point, we also can't say what would be the optimal methodology, just because both of them develop for us in parallel. As soon as one improves, we can improve on the other one. In computer vision, things like ImageNet have incredibly accelerated the development of deep learning. Some simulation environments such as like OpenAI Gym and Mojoko have really accelerated deep reinforcement learning. And this kind of parallel progress moves on like this. So essentially what I can now do is ask a final question or give another audience member a final chance to ask a question, because I think so far we've been sticking pretty much to our script here, and we're trying to make this interactive. Is there anyone who would like to ask a question? I can again check if there's any raised hands. If that is not the case, then we can move on to a final, very hypothetical question. So we've been talking about very different aspects of. Oh,
sorry, there's someone who just raised a hand. Yeah.
Oh, I really don't like the Zoom interface. Sorry, Krishna, I did not see this.
Hi. So I hope you can hear me. And my question to the panelists is, we've been talking about how data is driving a lot of progress for all of the other, computer vision and other domains, but for at least things that involve real world, data sets or simulations, we need accurate physical models or accurate material properties and things like that. What do you think is the best way to go about collecting data in this aspect, like data that's physically plausible or accurate? Like, you have lots of models for computer vision or 3D CAD models, but they don't have physical properties, which greatly limits their applicability.
Does anyone want to take a stab?
So I'm going to kind of dodge the question a little bit, and I'm going to basically say that I think that a simulator doesn't necessarily have to be accurate or complete in order to be useful. And I think the interesting question in my mind is, how do you take something which is clearly has some sort of useful information in it? Like, how do you take a maybe simplified simulator or something which doesn't have the correct dynamics or something like this, and combine it with real data in order to ultimately get something useful? I don't necessarily know how to do that well, but I think this is a very interesting research topic in my mind. So using very simplified models or simplified simulators, or simulators that we know are biased or wrong, in order to accelerate learning, or how to use learning to augment these things in order to get better policies or better performance on a task. Again, I don't know the answer to that question, but I think that's an important one.
So I have a different answer, which is why to start with CAD models in the first place, right? So one of the things that you can do, right, is, we have our robots out there, right, all the time. So you can collect a lot of unlabeled data, and you can observe the real world, and you can use reconstructions of these things that you observe in order to create your simulation. And by definition, those things will actually have the properties of the real world. And then you can combine those assets, say the static part of the background as well as the dynamic objects, to regenerate millions, billions of simulations. And then the question doesn't arise because inherently you already have the physical properties of those objects. And this is you can mix with real logs, you can do augmented reality, all these things. This is the strategy that we are going for. And this allows you to not need to have material properties and other things in your CAD models that is very, very cumbersome. And also you can have much better fidelity gap, so much smaller fidelity gap than if you use just artist-generated stuff.
All right, thank you. I was just going to ask another question, but Nicholas, jump in.
Hi, I'm Nicholas. I'm one of the co-organizers. Unfortunately, I joined a little bit late. I'm also a research scientist at DeepMind. So one question that I've asked repeatedly throughout the conference so far in various workshop sessions, I guess, is also related to simulation. I'm kind of wondering whether if we work a lot on hardware, we are sort of a bit too bottom up in some ways. If sort of with the kinds of problems that we can tackle, and whether sort of apart from sort of using approximate simulators to inform our behavior in the real world, which is obviously sort of very, very valuable, also sort of from a methodological perspective, shouldn't be looking more at sort of perhaps more complicated problems in simulation to study sort of questions such as, I don't know, behavioral hierarchy, and maybe questions around meta learning, sort of where it comes to richer task diversity, just because these are actually incredibly hard to study in the real world to create sort of the appropriate setup for this. And if we sort of try to do it on the robot directly, we would almost maybe lose, in most cases, not in all cases, many of the problems that we actually care about, because we would basically be in a sort of, in terms, for instance, task diversity or the richness of the behavior space that maybe that the robot can express, we would be in such a restricted setting necessarily because of the limitations of the hardware, because of other sort of practical constraints. So I was wondering what people think about this.
Okay, thank you very much, Peter, and it was great to have you. For the other panelists, we know it is now 8 p.m. in the UK. If you can stay on and answer this question, that would be fantastic. Otherwise, it would be it was really great to have you join us, and yeah, we would hope to see you again in a future workshop. But if you have some time, please go ahead.
So I think this is a very reasonable way to leverage simulation, and I think it makes sense to study problems like meta learning and things like this in simulation. Again, in my opinion, I think this kind of accords fairly well with one of the points I was making earlier about cost of collecting data and cost of designing something. So I think simulators are a great way to, essentially generate data based on, our knowledge of physics and geometry and the sort of formalized scientific knowledge without having to actually run things on real robots. So that's my perspective on it, but I think this is a very reasonable thing to do with simulators.
I would say that it kind of depends on which domain you're in. of whether you need simulation to achieve those things. So Raquel posed the idea that we're going to have perfect real to sim. And then why do we need sim? You know, or why do we need to be designing handcrafting simulation environments? And it might be that there are domains where that's possible. You know, object detectors for self-driving cars are really good, and there's infinite driving data. And so maybe in that kind of domain, it's possible to go real to sim and then have enough data to understand higher level interactions between objects and things like that. But there's going to be other domains where the real sim problem is really hard, in which case you've got to design your scenarios you're running from in sim directly. Anyway, so I think it depends on what kind of scenario you're in, of what kinds of methods you need to use. I'm also going to drop out. Thank you.
Thanks, Thomas.
Thank you very much.
I mean, we could go ahead and with the panel session, sorry, the poster session as well. Like I can share my screen and we can go over the posters for the second session if that works.
All right, I got to head out. Thanks a lot, everyone.
Thanks again, Byron. Thanks for joining.
All right, see you. Thanks.
Okay, so I'm going to share my screen quickly and then great. So I think for the okay, so wait, I think we did this already, did we?
Oh no, I haven't. Not yet.
Oh, okay, sorry. Go ahead.
Hi everybody. Just to give you a very quick overview of this this paper, the main goal is to learn visual motor policies in simulation and transfer them to the real world, specifically the context of drone racing. And instead of using techniques such as domain randomization, which are quite popular, but have the downside of being practically open loop because you don't know how much diversity or how much data you need to actually have robust transfer. The key idea behind this paper is to use multiple modalities of data. So we train a cross-modal representation that can robustly go from simulation to the real world for drone racing. And if you're interested in more details, please see me at the poster session.
Thanks. This is menu on.
You hear me?
Yeah.
So hello everyone. I'm presenting this work on learning topological motion primitives for not planning, where we basically propose a hierarchical approach for planning and control to tie knots on the table. The contribution of this is that knotting tasks are typically very complex, and sampling-based methods typically take a few hours to make a plan. So we decompose knotting tasks into a shared collection of steps and learn how to implement each step as robot motions. So if you're interested, come to our poster.
Sorry, before we go to the next one, can everyone see the screen that I'm sharing?
Yes.
Oh, okay. Yeah, the next one is Achin Jain.
Hi everyone, this is Achin. So I'll discuss our work on Bayes race, learning to race autonomously using prior experience. We basically present an approach for learning-based model predictive control for autonomous racing that reduces the effort for system identification. So when we talk about MPC for autonomous racing, we often need to spend too much time, or we need to worry too much about tuning the dynamic bicycle model. And our approach essentially allows you to start with the simple, easy to tune kinematic model and then reduce the mismatch between the predictions and the true dynamics by learning from the onboard sensor measurements. Yeah, happy to discuss our work during the poster session.
Right, next is Sasha.
Hi, I'm Sasha Lambert. So in our workshop paper, we look at MPC, or model predictive control, as a Bayesian inference problem, where we are trying to find the optimal distribution over control parameters, which can be complex and often multimodal. And in our approach, we use recent developments in variational inference to approximate this distribution as a set of particles. And we show that you can introduce structure into this method, into the posterior, to get these approaches to scale to high dimensional robotics problems.
Great, thanks. Next is Tejas.
Yeah, hello everyone. Our work is learning rewards via state marginal matching. And we derive a new method for inverse reinforcement learning to recover both reward and policy by specifying the expert state density through minimizing the NF divergence in state marginal. And the previous work on state marginal matching cannot learn the reward. We show empirical results on the goal-reaching robotic simulation tasks. See you on poster session. Thanks.
Awesome. Next is Gilvu.
Hi everyone, 1 second. Yeah, I'll be presenting a scalable Bayesian reinforcement learning algorithm called Bayesian residual policy optimization. We formulate robotic tasks with model uncertainty as Bayesian reinforcement learning. And the structure and scalability comes from leveraging the experts who assume to know the latent model sampled from the distribution. Our agent starts learning from the expert ensemble and makes corrections, and therefore learns very quickly in a data efficient manner. We prove that the agent is guaranteed to make monotonic improvements and verify this in various robotic tasks. Thank you.
Awesome. Next is Samuel. I guess this paper was already, I guess they presented in the first poster session. So that's pretty much it. Again, the link to GatherTown is posted on the chat window, so you can just click on it to just join the GatherTown session. And thanks so much for joining the workshop, everyone. I think that's probably, I don't think we're gonna have more in the Zoom session after the GatherTown session. So thanks for joining.